Get started, everyone. It's my pleasure to kick off our guest series. And the very first speaker is Yann Dubois. He's a final year PhD candidate at Stanford University in computer science, co-advised by Percy Yang and Katsuo Hashimoto. His research focuses on improving the effectiveness of AI when resources are scarce. And more recently, he has been part of the Alpaca team working on training and evaluating language models more efficiently using other LLMs. And that is what his talk is going to be about. Welcome, Yann, and I'll hand it over to you.
Great. Well, thanks for having me. Then we can get started. One thing is, if you have questions, maybe wait until the end, simply because there's a lot of people. So it's going to be easier, I think, if we just have questions at the end. So yeah, but if there's something that is really unclear or if my mic stopped working, you can, of course, start, tell me, because I don't actually see any of the messages. Great. So let's get started. So I'll be talking about scalable evaluation of large language models. So as many of you know, you all know about LLMs, given that you're in this class, and LLMs are all over the news. So those are some of the applications that you might have interacted with LLMs. And what I'll be talking about is how do you evaluate their performance. So first, I'll give you a quick overview of evaluation of LLMs and evaluation generally in AI. So why is evaluation important, and what is evaluation? So when you develop an AI pipeline or an LLM, you usually have a goal in mind. So evaluation is simply quantifying the progress that you're making towards that goal. And why is that useful? I'll give you a few examples. One thing that you can do with evaluation is that you can identify improvements that you could do in your model development pipeline. So you can understand how to better design models. Another thing which evaluation is useful for is if you ever used LLMs or open source LLMs, you will see that there are hundreds, if not thousands of LLMs out there. So it will allow you to select the best model for your own use case. Another reason why evaluation is important is that even if you already selected the best possible model, you might not know whether this model is good enough to be put in production, or if whether your entire AI application or your entire AI system is ready to be put in production. So evaluation tells you also, you can have some threshold, and it can tell you or make you confident that your model or your AI pipeline is good enough to be put in production. So those are some of the things for which evaluation is useful. Great. So evaluation, there's a lot of desired properties that we would want our evaluation pipelines to have. I'll briefly mention a few of them. This is definitely not exhaustive. One thing is scalability. So this is actually in the title of my talk. Scalability is really important because we usually call these evaluation pipelines many times, and I'll show some examples later. So if you call these evaluation pipelines many times, for example, when developing a model, you really don't want to be waiting too long and also spending too much money for every call that you do to your evaluation pipeline. Another thing is relevance. Of course, you don't want to evaluate things that are completely irrelevant to your application or to your use case. Maybe something like discriminative power. So what I mean by this is that you want your evaluation pipeline to be able to discriminate between models in a very fine-grained way. So what that means is that usually you want your evaluation pipelines to be complicated enough to, for example, distinguish between a Llama 7TB and a Llama 7B. If not, it's not that useful. But if it's too hard and all the models are not performing well at all, and basically they're all random, it's not useful either. So there's a fine balance between kind of simplicity and complexity of the pipeline, which depends on the current models, to be able to discriminate between different models. Another thing is interpretability. If your evaluation pipeline is very interpretable, then you can take action on it, which is very useful, for example, for model development, to know what are the things that you should be changing. Reproducibility, this is really important, for example, in academia, where we keep kind of citing the same numbers, and you definitely want these numbers to be reproducible. And you want, in a very broad way, your evaluations to kind of not be biased. And I'll talk about these things in more details later. The actual desiderata or the actual desired properties really depend on what you're going to use your benchmarks for. So one thing I really want to emphasize here is that, as I already mentioned briefly before, there are a few different use cases of evaluation pipelines. And for different use cases, you will have different desired properties. There's definitely not a single kind of evaluation pipeline that will be perfect for all your use cases. And you have to think every time that you develop you build your own evaluation, or when you choose what evaluation to use, you should really be thinking, what are the properties that I want in my own evaluation? Why am I actually evaluating my models? For example, if your goal is development, for example, for knowing how to improve your model, then scalability is really important. Because, for example, when you do development, I'm sure you have some experience with hyperparameter tuning and just training machine learning models. When you do hyperparameter tuning, you need to call basically a benchmark or some evaluation pipeline every time you try a new hyperparameter. So that's going to be very expensive if your evaluation pipeline is expensive. Another thing which I already mentioned is that you want discriminative power. And when you do model development, by changing your learning rate by a few, like 1e minus 4, 1e minus 5, it's going to make a very small difference. So you definitely want your evaluation pipeline to show that difference. If it's for academic benchmarking, which I'll talk about later, I already said reproducibility is crucial. Another thing which is important is robust to gamification. So what I mean by this is that there will be many people when you release an academic benchmark, there will be many people who will try to publish papers and kind of optimize the model for your benchmark. So you don't want them to be able to really game your benchmark in some ways. If a goal is kind of develop an application and maybe to put it in production, then interpretability is really important. You want to know what is going wrong. You need to trust your pipeline, because if you actually making a decision on whether to put something in production, you need to make sure that your evaluation pipeline is trustworthy. And relevance. Of course, if your application is, for example, in coding, it's really important that you actually evaluate coding instead of, for example, math. So those are just a few desired properties. And really what I want to emphasize here is that there are many different properties. You will never find a single evaluation pipeline that will have all these properties. So when you develop your own LLM, or when you use your own LLM or evaluate your own LLM, you should be thinking about, why am I doing actually evaluation and what are the things that I need? And you will have different benchmarks that will be good for different properties. And I'll be talking about a few of those benchmarks. So evaluation recipe, the recipe to build an evaluation pipeline is actually very simple at a high level. The high level is that you need to decide an evaluation data set. So you need to select an evaluation data set. So you can think about it as some questions to the LLM and maybe some additional information. So some benchmarks will require, for example, the gold answer. So this is just the data set. And then the other thing which you really need to have is the evaluation metric. So by this, I mean, for every example, you need a way to quantify how good the answer of your LLM or of any AI pipeline is on that single example. And usually when you have these two, what happens is that you take every example, you quantify the performance of the output of your AI model on this example, and then you aggregate it over your entire data set. Typically, the aggregation is just averaging. So classic AI evaluations, I want to just set the stage a little bit, and then I'll talk about why LLM evaluation is actually a little bit challenging. So in classic AI evaluation, you usually have a very clear task in mind. So for example, if you're building a dog classifier, the task is classification of whether there's a dog in an image or not. So here, it's very easy to decide what data to use for evaluating. It's basically data that is very similar to the data that you will encounter, that your AI model will encounter when deployed in the real world. So you will try to find ID data from the test data that you will actually encounter in the real world. So basically, all that means is that you will want to have images of things you want to classify, whether there are dogs or no dogs in those images. In terms of metrics, usually these tasks in classic AI evaluation are what we call close-ended. So close-ended means that there's a limited amount of possible answers. For example, in classification, there's really, at least dog classification, there's really only two answers. Either there's a dog or no dog. So there's only very few possible answers. And the solutions are usually known and objective. So in this particular case, is there a dog? Yes, there is. It's a clear and objective solution. And as a result, finding metrics or building metrics is actually very easy because you have this close-ended task. The only thing you need to do is, for example, you predict whether there's a dog in this image. So this is the prediction from your model. You simply compare whether you were correct or not. If you were correct, you get a 1. If you were not correct, you get a 0. And then you average this loss or this metric over your entire instruction set or entire data set, and you get this accuracy. So in this case, you have an accuracy of 0. So the fact that you have very clear tasks with close-ended that are close-ended means that it's very easy to build automated benchmarks. And automated means also scalable benchmarks. So how is that different with LLMs? So with LLMs, there's a very large set of tasks that people will use LLMs for. So this is just an example for Instruct GPT, which is basically the precursor of ChatGPT. And you see that people use it for generation, for open question answering, brainstorming, chat, rewriting. And really, there's so many things that people could ask to these models. And not only this, the actual task or this distribution of tasks is usually not known when developing the model. So if I'm developing my own model and I will just release it, for example, on Hugging Face, I have no idea what people will use it for. So it's actually really complicated because you don't know what people will use it for. And not only do you not know what people will use it for, but also the task that people will use it for will usually depend on the quality of the model. So if the model is really good, maybe if it's really good at summarization, maybe they will use it more for summarization. So there's this tight dependency, which makes it hard for building evaluation pipelines because you don't know what is the real task. The other thing is that it's open-ended tasks. I have a chat question. Oh, I think someone is asking, yeah, about the volume. I'll continue. So another thing is that it's open-ended tasks. So what I mean by this is that instead of this image classification where you have a single possible label, here when I'm sure many of you have interacted with ChatGPT, the type of question that you will ask might have many different answers. So for example, here I just gave one example that I found online where someone asks ChatGPT to find 3 Instagram or to write 3 Instagram story ideas for a plumbing company relevant to blah, 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 and it is informative and educational, but still fun. There's clearly no right answer. There are many possible answers, and you cannot even enumerate all the possible answers. And there's a continuum of quality. It's not as if there's one right answer and one wrong answer. There are many possible answers that are on this continuum of quality. And not only is it on this continuum of quality, but also people might disagree. For example, I might think that the first answer is better, while someone else might think that the second answer is actually better. So that makes it very hard to evaluate LLMs and to build automated benchmarks. So I'll be talking about basically how do we overcome this challenge of having this diverse set of tasks, and more importantly, having this open-ended tasks. Great. So as I said before, there are 2 things that you have to think about when building an evaluation pipeline or benchmark. First one is what instructions do you use, and the other one is the metrics that you use. In terms of instructions, really, I'm not going to give you any smart idea here. I might a little bit at the end, but really what people end up doing is kind of brute forcing their way. So what I mean by this is that they will just try to collect as many representative instructions or questions to an LLM as possible, and kind of cover as many tasks or as many potential tasks as possible. that will be representative of what this LLM will be used downstream. So there's really nothing smart down here, although I'll mention maybe some recent ideas in the community later. So I'm going to focus a lot on the metrics that you use. So as I said, the challenge is that it's open-ended. So now I'll talk about a few ways to bypass this challenge or overcome this challenge. The first one is actually to convert this open-ended task into a closed-ended task. So basically to bring it back closer to classical evaluation of AI models. So for example, what you could do is instead of asking, so if you want to ask some questions about supernovas, instead of asking a free-form text about supernovas, you can ask it some multiple choice question. You could ask ChatGPT, hey, is it true for type 1a supernovas? And then you ask there are a few choices, and you ask ChatGPT to say which one is true. So that will constrain the type of outputs that you can give. And now this is much easier to evaluate, because now, given that it's not a free-form text, you can just say you can just check whether the correct answer, because you can just know what the correct answer is. You can collect that, and you can just check whether the correct answer is the same one as the answer that is provided by the model. So usually how this is actually done, I'll talk about it later, but it's that you take an LLM and you basically look at the likelihood of generating these 4 sentences, and you just check which one gives the LLM, for which of these choices does the LLM give the highest likelihood. So in other words, what choice is the LLM most likely to generate? And then you can just compare the best, like the most likely generation with the correct answer. So this is this idea of converting it to closed-ended task. The benefits of doing it that way is that it's very scalable and you really understand what is going on. The downside is that now you change the task. You went from an open-ended free-form text to something that is closed-ended with only a few choices. So that will basically, you will evaluate something a little bit different than how the models will be used in practice. Great. So a second option is to use what is called reference-based heuristics. So by reference-based, what I mean is that you can collect a real answer. So to every question, you can collect a potential solution as given by some human or by some expert. So for example, here I don't even know what the question is, but here's the answer that is the reference one. So imagine that the question, I don't even know what the question was, but maybe the human says that the right answer is they walked to the grocery store, and the generated answer is the woman went to the hardware store. Then what you can do is you can start comparing or asking yourself how similar is the answer generated by the LLM to the answer collected by the human, so the potential answer. So there are many potential metrics there. So usually how these are done, for example, bleu and rouge, if you ever heard about those are more classical, I would say, evaluation metrics. What they do is that they check the n-grams. So that means they check the presence of multiple words that are next to each other. For example, to the appears in both sentences, and it looks either at the recall or the precision of basically how many n-grams are in this sentence that are also in this sentence. Another one is BERT score, which would basically take a BERT model. So you can just think about embedding this entire sentence into some vector representation that retains a semantic similarity and does the same thing for the reference and just checks whether the two are similar or not. So another way, this reference-based heuristic, what it does is that it doesn't even look at the question. All it does is that it collects for every question a potential answer, and it tries to compare the generated answer with the potential human answer. So in some ways, it tries to do the same thing as with accuracy, but instead of using a hard metric like the 0-1 loss, which means either you have a 1 if it's completely correct or a 0 if it's not, it tries to use some smoothened version by looking at the similarity between the two sentences. The benefit is that you didn't change the task here. The downside So we still have free-form generations. The downside here is that there are many potential solutions. So here that would work actually pretty well if this reference answer was the only potential answer. But in reality, if you go back to the previous example I showed you where you have to generate Instagram stories, there are many potential solutions, and there might be one very good solution that is actually very different than the one that the human wrote. So as a result, using these type of metrics might wrongly tell you that your answer is completely wrong when actually it's a great answer. So just think about it as like writing a book. Maybe the human wrote one type of book while the LM wrote a different type of book. So when you look at this similarity between the two books, it's actually going to be very low, even though the book might be great. Great. So another potential thing for metrics is to ask, another potential way of dealing with this problem is to simply ask humans to evaluate the output of the models. So you could just think about it as humans look at the questions and the answers, and they just say how good the answers are. So the benefit is that this is really the desired kind of evaluation in the sense that you didn't change any of the tasks that you're performing. The downside is that this is really not scalable because now you need to have humans that are in the loop and they really read every possible answer of your model or all the answers given by your model. The other downside is that it's also not reproducible because humans have very high variance. So you will get very different results every time you use a different human for annotation. And finally, one aspect that I'll talk about a lot about in this talk is that you can try to make the the human evaluation more scalable by instead of asking humans to evaluate the answer, you can ask LLMs. So you can ask, for example, ChatGPT, hey, ChatGPT, here's the question given to, I don't know, this Llama 7B, here's the answer. How good is this answer for this question? The benefit is that we still didn't change the task, and now it's very scalable. The downside is that some people, at least currently, there's a lack of trust, I would say, in these model evaluating other models. You also don't have much interpretability. You don't really know what the LM is evaluating. And also it requires, oh, someone is drawing. Also, it requires an Oracle LLM. So you require having a more powerful LLM for doing the evaluation, which means that you cannot really use, at least not how I said it this way, this type of evaluation for evaluating the state-of-the-art model. Okay. Oh, how do I remove? Oh, okay, I still see the drawing and I don't know how to remove that. Oh, thanks. Great. So now I'll talk about, now that we saw this overview on evaluation of LMs, I'll talk a little bit about some of the LMs that are open and that people use in the open source community and in the academic community. So usually in the academic and open source community, I would say that benchmarks are really used for evaluating a broad set of performance. So for example, think about it as having the different open models and maybe ChatGPT, maybe like GPT-4 and some Claude models, and you want to know which one is the best possible model at this point. So you really want to have a broad evaluation of the quality of a model. And use cases, well, as I said before, it might be used for development. So when you develop your own model, you want to know how well you're performing on a broad set of tasks. Model selection. So if you build a new application and you really don't know where to start with, like which model to start because there are so many choices, you might just take the one that is the best on the current benchmarks. And also a lot of people use, or a lot of companies use these benchmarks for kind of PR. So they say, hey, look, you should use our models because they are the top ones on this benchmark. So I'll talk about a few potential ways that people do evaluation in the open source community and academic community. One is simply looking at Perplexity. So hopefully you all know what Perplexity is, but if not, I'll actually give a brief I'll briefly overview what Perplexity is. The second option that I'll talk about is what I call closed-ended kitchen sink. So that means basically take all the closed-ended tasks that you might perform and just evaluate your model on all of them, thinking that basically if you cover so many potential close-ended tasks, and your model is good at all of them, it's probably good at your own task too. Another one is just having some chat with humans. So this is this human evaluation thing that I talked about before. And the last one is this LLM-based evaluation. And that's what I'll talk most about. Great. So Perplexity. So one thing which is definitely used in the academic community and even actually in companies, it's just that people don't really show the numbers, is looking at Perplexity, which is essentially looking at pre-training validation loss. So I don't know how much you saw already in this class, but basically these LLMs are trained to maximize the likelihood of the generated text. And the loss that you use is this cross entropy loss, which is simply generating, basically giving the likelihood of generating the next token given the previous tokens. And Perplexity is simply a more interpretable version of this validation loss, where instead of taking just the loss, you take the average of the loss over the entire sentence. This is essentially to make your loss independent or somewhat independent of the length of the sentence that was generated. And then you take this exponentiation here. So 2 to the power of the average loss. And this is because you want the loss to be essentially independent of the base that you're using in your log loss. So Perplexity is essentially between 1 and the size of the vocabulary. It can actually go higher, but like for most models, it will be between 1 and the vocabulary size. And the intuition that you should have of Perplexity is that it basically tells you the number of tokens that your LLM is estimating between. So if your model is really not sure between 2 words, you will basically have a Perplexity of 2. So here is the test Perplexity of different models between 2017 and 2023. I believe it's on Wikipedia. So I just wanted to give you a sense of like the Perplexity numbers. Basically between 2017 and 2023, the models went from 70-ish Perplexity to less than 10. So that means that models right now are estimating every time they want to generate a Wikipedia word, they are estimating between essentially 10 words. So they're pretty confident on 10 potential words for every new token that they're generating. So I see a question, does it take into account the embeddings of the words? So I don't quite know what you mean by the embedding of the word here, but basically this is dependent on the tokenizer. So I'll actually mention that really briefly later. So Perplexity is not used and not that much used for academic benchmarking, but it's actually really common for model development. So especially when you do pre-training, the loss that you're trying to minimize is the Perplexity or your validation Perplexity. So this is very common. It's just that people don't show these numbers anymore. And the reason why they don't show it anymore is because it actually really depends on what data you're training on. If the training set, if your validation set, or if the set that you're using for computing your Perplexity is in your training set, then you will get very low Perplexity. So that's one problem. The other problem, as this question kind of just alluded to, is that the Perplexity depends on the tokenizer that you're using, which means that when different models use different tokenizers, as is the case, then you really can't compare between models. So this is only really useful for kind of model development where you have a fixed tokenizer. So why is Perplexity still useful? Basically, Perplexity is extremely highly correlated with downstream performance. So in general, the lower the Perplexity, the better you will do on most downstream performance. It's actually very hard to find data sets or benchmarks on which better Perplexity will lead to worse results. But as I said, it depends on the data and the tokenizer, which is why people don't really use Perplexity, or at least they use it internally, but they don't show it externally, the numbers that they get. So the pro or the benefit of Perplexity is that it's very simple to compute and you know exactly what you're computing. The downside is that it's actually looking at a different kind of task, which is just generating the next token which is different than how we're going to actually use these models, which is for this free-form type of generation. And as I just said, you can't compare between different models because it depends on what data they were pre-trained on and also what tokenizer they use. Yeah, as mentioned in the chat, yeah, different tokenizers will have different questions. Yes, I will send the slides later. Sorry, different tokenizers will have different number of different vocabulary size. Great. So close-ended kitchen sink. So I already mentioned about, I already talked about Perplexity. As I said, after this, another kind of way that people are evaluating these LLMs is just to look at all possible kind of tasks that are pretty good and that are easy to evaluate. So they are close-ended. So I would say that there are two, I mean, there are a little bit more than that, but there are two main kind of close-ended kitchen sink or these aggregated benchmarks of many different benchmarks. One is Helm, and the other one is Hugging Face OpenLLM leaderboard. And basically what they do is that they just take many different benchmarks that were released in the open source, and they basically average, or they look at the average result on all these benchmarks, and they kind of just choose how to average stuff and which benchmarks they should include and which benchmarks they should not. So I'll talk about the OpenLLM leaderboard because this is really what is used the most, at least in the open source community. And there's also a new version that came out, I believe, 2 months ago. So I'll talk about the new version, and then I'll briefly say why they actually had to change it. So I'll give a few examples of data sets or benchmarks that are in this OpenLLM v2. So this new version of the Hugging Face OpenLLM leaderboard. So one of them is what is called MMLU Pro. So what this does is it tries to evaluate the knowledge of your model. So this is just one example that I'm giving. So this is an example from this benchmark. The gypsy moth produces, so that's the question. The gypsy moth produces a natural attractant, blah, 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 blah. And then it tries to ask what quantity of attractant will diffuse through the orifice in the same amount of time. And you have to do basically some simple math, I believe, and yeah, have some knowledge about chemistry. And there are 10 potential options. And you know the correct answer is I, so this one, this out of 10. So as we saw before, this is multiple choice question, which means that it's actually very easy to evaluate this benchmark, because all you have to do is take a model, look at the likelihood of generating each of these choices, and just choose the most likely choice, and then just do basically the accuracy or the 0-1 loss between the most likely choice as generated by the model, decided by the model, and the correct answer. So the reason why this is called MMLU Pro is that this is a more this is a new version of what is called MMLU, which was a previous benchmark. MMLU is really the most common, I would say, knowledge benchmark. So it has many different kind of university, maybe undergrad level questions in chemistry and biology and many different domains. And the reason why people had to go to MMLU Pro is that the newer models are doing too well on MMLU, and basically it reached the level of essentially human performance, which means given that these benchmarks are usually a little bit noisy, so there might be some wrong answers, that's the best we can do on MMLU. So this is a less noisy data set that is harder. And what type of questions people ask, or what are the questions in this MMLU Pro? It's a lot of math, physics, chemistry, law, and some engineering, and like really tries to cover as many possible domains as possible. And this is, as I said, really about knowledge. So yeah, this is this MMLU Pro. Great. Another data set that is in this OpenLLM v2 benchmark is also about knowledge, or measuring knowledge of these models. This is called GPQA. So this is for questions that are supposed to be written. So they're all written by experts, they are supposed to be hard for non-experts that are, even if they use Google. So basically, they try to find questions or to write questions such that non-experts that search on Google for like 30 minutes cannot find the answer to this question. So this covers 3 domains: biology, chemistry, and physics. And this is one example here where it's about quantum mechanics, and there are 4 potential answers. And I mean, I definitely don't know the answer just by looking at this question. And it's supposed to be that I wouldn't be able to find the answer in 30 minutes on Google or on the web, even if I tried to. Yeah, so this is this other benchmark. So those, again, are all the benchmarks in the OpenLM v2 leaderboard. Another one is called MU-SR. This is about reasoning and long context reasoning, actually. So this is a benchmark that is automatically generated. I actually cut this example because it's around 1,000 words for every instruction or for every question, so it's very long. And it's essentially about murder mysteries, some object placement question, and some team allocation optimization. So here, for example, for the murder mystery, there's an entire a few paragraphs essentially explaining the background of the murder, and then it just asks who is the most likely murderer. And the way it's generated is that there's a lot of information about this murder case, and they try to remove automatically part of the information and then generate an entire text based on this removed information, or the information that's remaining. Okay, another one is the math data set. So this is high school level math. So the question is, here the problem, just to give you one example, the equation x squared plus 2x equal I has 2 complex solutions, determine the product of their real parts. And the solution here, the only thing that matters is the thing that is in the box. So what they do is that they simply compare between the solution from the box in the real human solution and the LLM generated solution in the box. Okay, so this is high school level math. Another one is called if-eval for instruction following evaluation. So this is actually a pretty interesting benchmark. This doesn't look at the content of the answers of the LLMs. So all it does is that in the instructions, so in the questions that they ask to the LLM, they have some formatting rules or some formatting instructions. So for example, let's just look at this prompt. Write a casual summary of the US maternity leave policy with 2 sections and at least 25 sentences. And how they will evaluate, so that is free-form generation. So the model will write a free-form answer. As we said, this is hard to evaluate a free-form answer. So what they will do is that they will not evaluate at all the content of the answer. They will just check whether it has at least 25 sentences and whether it has 2 sections. So basically, we'll just check whether the formatting is correct, which I find very interesting because it basically sidesteps the problem of evaluating the content of this response being hard. So it just looks at the actual instruction following ability of the model for formatting. So yeah. So basically, if you look at this and also maybe MMLU Pro, then you will hopefully have some very orthogonal type of benchmarks. This one is more about formatting instructions, and the other one is about knowledge. Another, and I believe it's the last one in OpenLM v2, is BBH for Big Bench Hard. So Big Bench is a big benchmark. You don't need to know about it. And they only took a challenging subset of 23 tasks. And here are some questions. This is still multiple choice question, although it has some few shot. It's not that important. The question is here, for example, which sentence has the correct adjective order? And you have to choose between these 2. Or which statement is sarcastic? And you have to choose between these 2, what is one word difference. So this is everything about OpenLM v2, I believe. So now you get a sense of all these benchmarks being artificially easy, in the sense that it's artificially easy to evaluate these benchmarks. So none of them actually evaluate the real thing that you care about. But given that there are many type of benchmarks that you're evaluating on, the hope is that you cover a lot of different aspects of what good LLM should be, what LLM should be good at. And as a result, if your LLMs are good on this meta benchmark, then they should be pretty good for your own task. So let me read. Oh, I don't see the messages anymore. Oh, here, chat. Okay, I'll since kitchen sink transform the question. Mason, yeah, you definitely need to look at potential biases. And actually, a lot of the benchmarks that were previously written, there are actually a lot of biases in these things where maybe, well, it's not even biases. Maybe the model finds some spurious correlation and finds that maybe, for example, the longer answer is the correct one. So you definitely need to analyze a lot of that. I'll talk about the problem that was mentioned right now later. So, okay, difference between V2 and V1, that changed a few months ago, as I said. They basically made they basically replaced some benchmarks with more challenging ones. So you had MMLU and now you have MMLU Pro. For math, you had GSM 8K and now you have math. And for another knowledge one, you had ARC and now you have GPQA. And so they basically made the benchmarks harder because the models were just becoming too good on V1. And they also started using a different aggregation. So before it used to just be average. So they used to average all these benchmarks. Now what they do is something slightly smarter. For example, in the case of BBH, there are only two choices, which means that really a random baseline would have 50% accuracy already, while for MMLU Pro, there are 10 choices, which means that a random baseline would have only 10% accuracy, so 90% error. So now they basically look at the difference between the random baseline accuracy and your real accuracy that you get for your model. And that's kind of the renormalized metric that they use. So in some way, you weight higher the ones where you have fewer choices. Okay, so closed-ended kitchen sink, just to close that part of the talk. The benefit is that it's very simple. As you see, we can go through every benchmark. We can understand what's happening. None of them are great, but hopefully together they kind of cover a lot of things that we want our models to be good at. The downside is that it really doesn't evaluate the thing that we care about, which is open-ended generation in the first place. So yeah, great. So I'll talk now about human evaluation, and I'll specifically talk about one very famous benchmark that is done with humans. And this is Chatbot Arena. So I'm sure many of you have heard about it. The idea is that you would have humans. So any of you can actually take place in this benchmark and be used as if the human annotators. You will interact with two models in a blinded way, which means that you don't know which model you're interacting with, and you will basically ask questions to these two models. And then you will have to say which of the two models is better, or like which of the answers from the two models is better. So they collect in this way a lot of different upvotes or a lot of different comparison. I believe, I mean, on this screenshot, it's 300,000, but that's probably from early this year or even last year. So they probably collected more than 1 million already now. So yes, that's just Chatbot Arena. The type of questions, just for you to get a sense of these things, the type of question that people ask in the Chatbot Arena are things like, what's the most popular item on the menu of a subway in Taiwan? Or make a trigger bot in GTA 5. And yeah, this is the type of question. So of course you get a very biased type of question because it's only people who actually know enough about LLMs or like are interested enough to interact with these LLMs. So it's not a biased type of distribution, but it's very interesting. So here's talking about this distribution. Here's a type of task that people, or instructions that people ask for these models. There's a lot of coding, a lot of technical and software related questions, which makes sense given it's people that are interested in LLMs, and there's some like role playing. Okay, so that's about Chatbot Arena. So human chat, the review of human chat, the benefit is that now it's finally evaluating open-ended task. So really now it's free-form generation. You just ask any question, you see the answer, and you just have to say which one is better. One of the downside is that it's hard to scale. So they were able to scale it because they basically allow anyone in the world essentially to interact with these models, but it still takes a very long time to get results on these models, and usually it's only the best models, or at least the models from the best company, from the famous companies, are essentially evaluated on this benchmark. Which means that if you're developing your own LLM at your place, you will definitely not have 100,000 people interact with your LLM for every new learning grade that you use. So you can really not use this for model development. Another downside, as we said, is that you have a very biased type of distribution of instructions that people ask to these models. But overall, it's a great benchmark. Okay, so now I'll talk about LM based, and this is probably what I'll talk for the most of the rest. Yeah, basically most of the rest of the talk. So here the idea is to try to take best of both worlds, right? Best of both worlds. Right now we saw humans, which is not scalable, but at least evaluates the thing that you want, and we saw these closed-ended evaluation, this kitchen sink, as I call it, of closed-ended evaluation that are scalable, but really don't evaluate the thing that you care about. So the idea of LLM-based evaluation is that you can try to make the human scalable by replacing the humans with another LLM. And for this, I'll talk about one paper that we wrote nearly 2 years ago, actually, or like 1.5 years ago, which is called AlpacaEval. So this is this benchmark, which is one of the most common benchmark used with LLM-based evaluation. So as I said, the goal is scaling human evaluation. So the background, just to give you a little bit of background, is that we were developing at the time the model which ended up being called Alpaca. So that was 2 years ago. So that was an instruction following model. So you can just think about it as some replication of ChatGPT, kind of very early on. We wanted to have a model, open source, that is somewhat similar to ChatGPT. So what do we need for this? One, to train an LLM or to train an instruction following LLM, you need some data. So I'm not going to talk too much about this, but basically we collected some data using another LLM also. Two, you need to have a base model. So we used Llama 1.7b. That's already a long time ago. And you need to have a loss, or like a loss that you're going to be optimizing. And we used a supervised loss. This is not that important. The thing which I want to highlight here is that once you have a data and you also have a way to train your model on this data, you then need to tune your learning rates. You need to tune all your hyperparameters. So you need to have some development benchmark to know which hyperparameter you should be using. And that's where our idea came to use basically an LLM for telling us whether the generations that we were getting from these models were good or not, and to use this as a proxy evaluation benchmark, essentially to know whether we're making some progress and which hyperparameters we should be using. And once we did all of this, that's how we got this Alpaca 7B model. So as I said, when you design a benchmark, you need to think about two things: the metric and the instructions. So let's talk about the metric. The metric is actually very easy. What we did is that we asked a question so you ask a question, this is an instruction. You then have two models. Let's say that the model that you want to evaluate is in blue. You ask this model to generate an answer to this question. So this is now open, a free-form generation. And you ask another baseline. So in our case, we use DaVinci Z03, which is an old OpenAI model, to generate also an answer. And then what we did is that we took these two answers and we asked another model, so think GPT-4, which of the two models were better. So we basically did exactly what Chatbot Arena does, but we did it with LLMs instead of a human. And then the LLM tells you which one is better, and then you reproduce this over your entire benchmark. So all this instruction set that I'll talk about later, and what you get is what we call this win rate. So it's the expected preference for this LLM, so this Oracle LLM. So in this case, GPT-4. It's the expected preference of GPT-4 between your base model answer. Sorry, between the model that you're evaluating and the base model or the baseline. So this is this expected probability of winning. So this is the win rate. And this is the metric that we use. So it's actually very easy to compute, and it's very scalable. So does that work? So one thing you might wonder is, well, like now you just basically ask LLMs to evaluate. How do you know that it's good at doing this job? So that was 2 years ago, actually, 1.5 years ago, this result. Here you see on the x-axis the price for 1,000 examples. So humans, we use mTurkist here. This is around $300 for 1,000 examples. And here on the y-axis, you see the human mode agreement. So whether a human agrees with the mode of, like, what is the agreement between one human and the mode of all the other humans. So basically, how much humans agree with each other. You actually see that the metric is very low, 66%. The reason why that is because actually, if you look at two answers that are very similar with a few words that are different, people will really not agree on which one is better. And there's a lot of variance. People might even disagree with themselves if you ask it today and like maybe the next day. So the task is just very noisy and very hard, very subjective. And GPT-4 got around like 65 or 64%. So that was again like 2 years ago, and we were able to kind of increase and improve this evaluator. So essentially, we were able to get LLM-based evaluators that are as good as humans in the sense that they agree as much as humans or even more with humans than humans themselves, but they are at least 30 times cheaper. And that was 2 years ago. Right now, actually, the current evaluator on the AlpacaEval leaderboard, the benchmark, is around here, which means that it's more than 100 times cheaper than humans and actually much better than humans at agreeing with other humans, which is pretty surprising, or could be surprising. And what is nice is that it actually keeps improving. So every time you will have a new model that is released by like OpenAI or a new cloud model or any other model, the best possible one will just use this, and basically this point will keep going to the top left. So this is one of the reasons why I'm really excited about LLM-based evaluation, is that given that they're already good now, they will keep improving. So it seems to be worth your time to spend on designing kind of these benchmarks. Great. So the instruction set. So here, our instructions are, there's 800 instructions. Here are a few examples. The instructions from AlpacaEval are honestly pretty easy, pretty simple, because they were designed for the models 2 years ago. So here's some question. What if Turing had not cracked the Enigma code during World War II? What would have happened? And like, is MFCC the same thing as Mel spectrogram, or what is the difference? Or like writing some rap song on a speech, or things like this. So how did we choose this instruction set? Well, we wanted to aggregate. We basically aggregated different data sets that we found online, and the way we did that is that we wanted to have instructions that allow you to distinguish between models. So as I said before, for model development, it's really important to have this distinguishability, or this ability to distinguish between models. So we wanted this. And another thing which we wanted is our instructions to be realistic. And of course, it's a question of what does realistic mean. So given that we had the Alpaca demo that we released 2 years ago, we had around 300,000 people who talked or who chatted with our model. So we had a lot of questions that people asked to this model. So that's kind of what we define as realistic. And the way I'm just gonna go briefly over this, but basically the way we did it is we chose instructions that allow you to distinguish between models. So here you see kind of p-values for like t-test p-values to tell you whether two models whether one model is better than another one, and you basically want to have your p-value very low. So the exact details are not that important, but basically you spend some time on the instructions and choosing instructions. Great. So the AlpacaEval benchmark. So right now, at least when we released it, the correlation between the AlpacaEval benchmark and the chatbot arena, which we decided was kind of this at least silver standard for evaluation, was around 94% correlation, or Spearman correlation. So it's pretty high. So that means that the ranking of models as given by humans, that is not very scalable, and the ranking given by this LLM is actually pretty high. And it's much more scalable. It takes less than $10 and 3 minutes to actually run this benchmark. And it had a decent amount of community uptake. So we already have kind of 200 models from the community that was submitted on the benchmark. So summary about AlpacaEval and more generally kind of LLM-based evaluation is that we use an LLM to scale evaluation of instruction following LLMs. The benefit is it's scalable, and actually, if you spend some time on doing things well, you can get high fidelity in the sense that they agree with humans. So the LLM judges agree with humans. So that all seems great. I want to talk about like some challenges about this entire kind of pipeline that we had or that we still have. So I'll talk about AlpacaEval length control, which is the next version of AlpacaEval, and what was the goal there, and what was the issue that we initially faced. So the issue was about decreasing spurious correlation. So we really talked briefly about spurious correlations before. So the background is that when we released AlpacaEval, actually 74% of the time, the LM preferred the answer that was longer. So basically, it has as a reminder, it has two answers, and you ask this model which one of the two is better, and 74% of the time it just prefers the longer one. That is not completely shocking in the sense that humans also prefer longer answers. Part of it is just that if you ask humans two possible answers and they don't want to spend too much time kind of evaluating the answers, they will just probably have some spurious correlations and just say, okay, the longer one is most likely better. Anyways, we had around 74% preference for longer outputs. So when we released the benchmark, so here you see on the x-axis time, and on the y-axis you see the average length of the top 10 models on our benchmark. When we released the benchmark, the average length was around 1,200 characters. And basically over time, and especially in 2024, we saw this huge bump. So basically the best models became longer and longer and longer, or at least the best model on our benchmark. And this seemed was very worrying, actually, very concerning in the sense that a lot of the models that were getting better in our leaderboard honestly weren't better once you interacted with them. So it seems that they were really kind of over-optimizing for length because either directly or indirectly, people had realized, or like the models had realized, that this benchmark has this spurious correlation for length. So basically, when you do hyperparameter tuning based on it, you end up having models that are much longer or that generate longer outputs. So I'll talk briefly about how we fixed that. So we took a causal perspective, which is that we ask ourselves, what would the metric be if the baseline and the model output, so the one that you're evaluating, had the same length? That's just a question that we ask ourselves. So another way to view this is you can take a causal graph. So this is the preference as given by AlpacaEval judge. The preference depends on the model that is generating the answer, on the instruction, but also on the length of the output. And the length of the output depends on the model itself. So basically, what we said is instead of looking at kind of this causal path through all these nodes, the only thing we care about is this direct path between model and preference. We don't want to take into account the causal path between length of output and preference. So the idea, or the way we did that, is just to use a regression analysis, which is a very standard technique in kind of statistics to deal with these type of problems. So specifically what we did is that we took we modeled AlpacaEval's preferences as a function of these three nodes: model, length of output, and instructions. So the exact form of the model that we use is not important, but we basically use a GLM. So just think about it as a logistic regression with some fancy features. And once we have this model, so this is a model that basically predicts what is the preference of AlpacaEval based on the name, or like which model you're evaluating, the length and the instruction. And once we have this model, we can simply ask this GLM, so this model, what would the preference had been if the baseline and the model output had the same length. So basically what you have to do is here you have this length component, which depends on the length of the output of the baseline model and the model that you're evaluating. You just have to set these two to the same, which means that all of this becomes 0, and all you end up predicting with is this simplified GLM. And this is what we call the Alpaca AlpacaEval length control preference. So just a quick summary, we first modeled AlpacaEval preferences based on model length instructions, and we essentially just dropped the length term to get the AlpacaEval length control preference. So this is the model of AlpacaEval preferences, and this is kind of this predicted preference if the baseline and the model outputs had the same length. So benefits of using this, well, actually I didn't talk that much about this GLM, but it retains a lot of nice mathematical properties, so it could still be interpreted as a win rate. So more importantly, basically it's still between 0 and 100, and it has a lot of nice properties of win rates. Another thing is that it's model independent. So what I mean by this is that every time you add a new model, you have to train a new GLM, but you don't need to retrain the GLMs or the models, the AlpacaEval length control win rates for the other models on the baseline, which means that every time someone submits a model, you're not changing the win rates of the other models, which would be pretty annoying in academia. And finally, it's easily extendable. So right now we only talked about this spurious correlation for length, but you can do the same. You can use a similar technique for many different spurious correlations, just by adding a new term in this GLM. Great. So all of this, let's see whether it actually works. So here, what I'm showing you is AlpacaEval. This was some metrics. This is the win rate for different models. And here I'm showing you on the right, what if I ask the model, just prompt it to provide more verbose answers? And what if I prompt it to provide more concise answers? And what you see is that the win rate actually has a huge variance. So for the same model, if I prompt it to be more verbose, it performs much better on AlpacaEval, at least the original version. So it has this huge variance. When you use this length controlled AlpacaEval, so this is the length control win rates, you see that it's very little variance. So here, just by prompting it to be verbose, you only go from 50 to 51.6 instead of 50 to 64.3. So it somewhat worked. It's in the sense that it's less biased. And somewhat surprisingly, or at least interestingly, that was not what we were optimizing for. But by doing this this length correlation, this length length control, we actually increased the Spearman correlation with Chat-Arena. So I told you before that AlpacaEval had around 95%, or sorry, 0.94 Spearman correlation, which was the highest with MT-Bench. Well, actually now with this length control AlpacaEval, we have 0.98 Spearman correlation with Chat-Arena, which means it's very, very highly correlated with Chat-Arena. And I believe, at least when we release it, I believe it's still the case. This benchmark is the highest, the one that has the highest correlation with Chat-Arena, which is this human ranking that we saw before. And here you also see some different benchmarks and how highly correlated they are with Chat-Arena. Great. So retrospective, they work. So here I'm showing you the same graph as before, but I'm showing you the additional part of the graph after AlpacaEval length controlled was actually released. And we see that just after it was released, basically the length of the top model really decreased. And now it seems to have been increasing a little bit again. So I would say it seems to have worked, but maybe it needs an update. I don't really know whether this is kind of true, truly better models or not. So I would have to check again, but it definitely seems to be better than before. Great. So summary, we basically used regression analysis to alleviate some spurious correlation in LLM-based evaluation. But a broader summary I want to share is that you really need to be careful when using these LLMs. I'm all in for using LLMs for evaluators, but there might be some issues, and you always need to be kind of on your toes and be ready for alleviating some of these issues. So benefits, it has less length bias, as we saw, and it actually ended up with higher correlation with humans. Great. So I talked about AlpacaEval and AlpacaEval length controlled. Another probably just as common benchmark that is based on LM judges is called MT-Bench. So MT is for multi-turn. So it's basically similar to AlpacaEval, but it's multi-turn. So AlpacaEval is single turn, which means that you ask one question to the model, and then after the answer, it stops. It also has good correlation, as we saw before. It has around 0.94 correlation with Chat-Arena, so slightly less than AlpacaEval, but very high. And the type of questions are things like first turn, compose an engaging travel blog post about a recent trip to Hawaii, blah, blah. And then second turn might be like, oh, rewrite now your previous response, start every sentence with the letter A. So it's actually pretty cool that it's about multi-turn. Great. So LLM-based evaluation. Pro is that it also evaluates the real thing you care about, so free-form generation. It's very scalable, and not only this, it will improve over time. So I think this is like one of the key things is that humans are kind of, I mean, our evaluation won't really improve over time, while these models, they keep improving, which means that it will become more scalable and higher quality. The downside is that there's some trust issue. As we saw, sometimes we maybe don't understand, or we might have missed some spurious correlation. So people always have some trust issue with some of the LLM-based evaluation. So this is something that as researchers, we need to improve. Another thing is that you need an Oracle LLM. It's actually pretty annoying because as I said, it's actually hard to use these evaluation based on LLMs for state-of-the-art LLMs because they cannot use a better LLM for developing their own. And not only this, you can also not use maybe LLM-based evaluation on domains where LLMs are really bad, for example, math. Also, we kind of, as humans, we kind of gave away our control, and now we're not really the ones that decide what is better and what is not. Now we're relying a lot on the LLMs. Okay, so based on what I just said, which is these pros and cons, I want to mention one additional project that I'm actually still working on. I want to give some kind of preview of results because I thought it would fit well with kind of how the community I think will be going and what it should be going towards, which is how to scale evaluation in cases of expert domains. As I said, this is preliminary results, so things might still change. As I just said, LLM-based evaluation, very scalable, requires Oracle LLMs, which is not good, lack control. So we basically give away control as humans. And another thing is that it lacks interpretability. So when we look at these four things, the reason why we have this pro and con is that really, or the reason why we have these cons is that we, as humans, we how do you say that? There are two things with evaluation. There's deciding what the correct answer is, and then there's actually applying it. And in this case, when we do LM-based evaluation like AlpacaEval, like MT bench, we basically put these two things together, and now the LMs are doing both. They decide what the correct answer is, and they basically apply it. So what I think we should be doing is kind of separating both. We should still have humans decide what a good answer is and how to apply the evaluation, but then we should just decide that the LMs are the ones that should be applying it. Like this will be scalable. So to be slightly more concrete, usually when you build a benchmark, as I just said before, you have you basically just use humans for one thing, which is writing instructions. What I'm suggesting is that you should also write humans or experts, when they write the instruction, they should also define how to evaluate answers on this instruction. So one way that you could do that is by writing a very detailed analytic rubric. So this is, for example, how it's done in education. For example, in different education levels, you might have these kind of analytic rubrics, which says, oh, here the 4 different axes that you should be considering. Here's how you get an excellent score at this, a fair score at that, a poor score at that. And this is a one-time cost. So this is basically writing the benchmark. And given that it's a one-time cost, you should still have humans write it, even though this is slow to write, much slower than writing the instructions. It's still only a one-time cost. And here, trust is key because this is defining how we're going to evaluate our benchmark. And once you have this, you can have you can have LLMs a condition on this kind of evaluation strategy written by experts. You have the LLMs applying the evaluation. So the reason why I think about it that way is that applying the evaluation is a recurrence cost. So here scalability is key. So what we'll essentially do is that we'll have humans do everything which is a one-time cost, or experts do everything which is a one-time cost, and then applying it at scale with LLMs. And the human effort will essentially be amortized over the entire benchmarks that we're going to apply. So here the LLM will just decide which axis has what score. So the benefit of this oh, maybe one before talking about benefits, I just want to mention that here there are actually many different possible ways. So I just talked about analytic rubrics, but there might be other ways of writing this evaluation guides. One possible way is to write like checklists, like just a list of questions to tell that the expert would say, oh, LM, you should actually consider all these things in the answer. Another one is to write the actual answer. So maybe the expert might write, oh, here's a potential answer, and here's what you should be looking at when evaluating the answer from the LM. We saw the analytic rubric, which is this like matrix, and maybe you can also have a kind of list of errors. So I don't know how it works at UPenn, but at least at Stanford, we use Gradescope, which has kind of these list of errors. And for every error, you get a score deduced. So that's how we grade classes or assignments at Stanford, and basically that's a potential thing you could do. So imagine I write an instruction, you end up writing like 30 potential errors and how to deduce scores and how much points to deduce if you make such mistake. So preliminary results. So this is actually on an expert machine learning benchmark that I wrote myself because I mean it's basically the only thing I'm somewhat of an expert in. And you see here the naive evaluation. So this is the Spearman correlation with the ranking as given by humans. Naive means that the models is not conditioned on anything. So this is basically empty bench and AlpacaEval. And all these four show when you condition on the checklist, the solution, the rubric, and kind of this list of errors. And what you see is that the Spearman correlation increases by a lot. Again, this is preliminary results. I'm still hoping that I can increase these things, but you already see a huge bump from less than 0.2 on this very hard machine learning data set to around like 0.6 Spearman correlation. And what is nice is that this gain is independent of what LM use for the evaluator. So here you see for Claude 3 Opus applying the evaluation GPT-4o, GPT-4 Mini, and things like this. Okay, great. So I'm done with academic and open benchmarks. I'll chat briefly about some challenges, and then I want to leave some time for questions. So challenges. Oh, I saw. So challenges with open benchmarks and kind of academic benchmarks. One of them that we haven't talked about is consistency. So actually, I told you before that when you have these multiple choice questions, it's very easy to evaluate, but that's not completely true. For example, the order, and I think one question alluded to that before, the order of the answers that you give or the choices that you give will really change the quality of the answer. Could really change the evaluation score that you get, depending on how you evaluate your model. That is only true not if you use this log likelihood way of evaluating that I told you about before, but for example, if you just ask the model, oh, is the correct answer A, B, C, or D? Then if you reorder A, B, C, or D, it might change the answer that you give. So consistency is an issue. To give you a very concrete example of challenges of consistency, so we talked about MMLU. So MMLU actually has different implementation in the sense that people use different prompts and different ways of evaluating the generations with MMLU, and you end up with very different scores. So just to give you an idea, I told you before, MMLU is this multiple choice question. You have the LM that choose the most likely answer. But what does it mean to choose the most likely answer? As I told you before, one thing you could do is just look at the likelihood of all potential answers and just say which one is the most likely. Another thing you could do is just ask the LM, is it A, B, C, or D? Which one is the correct answer? Another thing you could do is also ask the LM to generate the entire answer. So just sample A, B, C, or D and see what it generates. But maybe what it ends up generating is something that has nothing to do with A, B, C, or D. Maybe it generates like E, or maybe it generates like zombie or something completely random. So depending on how you decide to evaluate your LM or to apply this or to decide what the correct generation is, you might get very different scores for your models. And actually, there used to be, now thankfully it's fixed. There used to be 3 different implementation of MLU: the Helm implementation, the original one, and the harness one, which is essentially the one from Hugging Face, the Hugging Face OpenLM leaderboard early on. And you see that the MMLU scores, for example, AMA 65B, was very different. So all this to say that even in this simple case of kind of closed-ended evaluation or closed-ended tasks, depending on how you prompt the model or how you decide what the correct answer is and how you should be sampling from it and stuff like this, you get really different scores. And people in the community usually, I mean, there will inevitably be some differences, and it might, it can be very annoying. Let's put it that way. Another challenge, which I think someone asked about before, is contamination. So here are a few tweets that point to contamination. So here, Harass says that in Codeforce benchmark, everything which was pre-2021, the models perform 10 out of 10, and everything which is recent, the models perform 0 out of 10. So that clearly points to the fact that this test set was actually in the training set of these LLMs, because pre-2021, the LLMs actually know perfectly the answers to that. So that's this type of contamination, which means that the models are actually trained on some of the tests or some of the benchmark, which is definitely not something we want. And here's another one where Suzanne just asked to Phi 1.5, which is an LLM, and it just asked to calculate the number of it asks to kind of generate the first question of the benchmark, and it's just able to generate the entire question of the benchmark, which clearly shows that the model was actually trained on that. Yeah. Sorry, I'm going to skip through. I saw your question on multi-turn. I'm going to skip through that because I want to go through the rest, but I'll talk about it during the question session. So for detecting contaminations, so as I said, contamination is a big problem. There are different ways you can try to detect that. One way is to look at the likelihood that is generated by the model. If the likelihood of the model is very high, so if the model is really certain about its answer, it kind of points to the fact that maybe it was in the pre-training set. So that's like one way. Another way, which I actually find very smart, is to do an exchangeability test. So the idea here is that most of the benchmarks online, they're always in the same order. So if you look at the likelihood of the canonical order of the benchmark or the shuffled order, if the likelihood changes, because every example should have no relation to the previous or next example, if the likelihood changes, then it means that it was actually trained or pre-trained on that data set, because it means that it saw the data set in exactly this order, even though really there should be no ordering in this benchmark. Example 1 could come after example 2. So if it gives a higher probability of example 1 coming before example 2, it means that it was likely in the pre-training set. That's some ways of detecting contamination. There are some ways for alleviating this. One way is to basically have a private test set that you never put online. Another way is to kind of have these dynamic test set. So this is, for example, what is done in Chat Arena, where humans kind of interact every time with this model and ask different questions. So this is dynamic. So if you constantly have different inputs, then you cannot have this contamination. Another challenge is saturation. So basically, very quickly, every time there's a benchmark that is used by the community, I would say in like 6 months, it ends up being completely saturated, or maybe not 6 months, but like at least 2 years. In between 6 months and 2 years become saturated. This is actually one of the reasons. This is the plot from OpenLM v1, and you see why they had to change to OpenLM v2, because basically all the benchmarks that they were using, they got saturated in less than a year. So here you see human baselines, and you basically see that for most of them, the best LLM reached a human baseline. And we actually had the same type of thing with AlpacaEval, where after 6 months, the models went from like 10% win rate to like 95, which is why we had to do a AlpacaEval 2.0. Other issue of benchmarking. So this is from a paper, I think at ACL, I can't remember exactly. So this is a paper that analyzes a paper that was submitted at ACL. And basically you see that most of the papers, so out of 461 papers, 69.4 look at English. So basically, honestly, most of the evaluations are essentially about English and about performance. So there are some multilingual benchmarks, which I linked to here. And I think more people should be looking at those. Okay, I think this is probably enough for now. And maybe one last thing, and then I'm gonna open it up for questions. One challenge, I would say the challenges of challenges, is that researchers are actually incentivized to keep the same benchmark, even if the benchmark is bad. And the reason why is because in every time we write a paper, we have to compare to previous results on the previous benchmarks, and then you're incentivized to basically always use the same type of benchmarks. So in 2019, which is pretty recent actually, 82% of papers in translation were still using BLEU, which is this metric that I briefly talked about before. But at this point, there were already so many better metrics. So yeah, so there's this issue that in academia we're kind of forced or incentivized to keep the same type of benchmarks, even if they're not great. Okay, so I'll skip through all the rest and happy to take some questions. So I'm going to read through questions now.
Thank you, Yann. Can we get a round of applause for Yann?
Okay, I see there's a bunch of questions already. So let me scroll up. So since kitchen thing transforms the question, okay, this I already talked about. Is there work to mitigate concerns with? Please write also the questions in the channel. Sorry, in the chat. I'm going to read them right now. Is there work to mitigate concerns with these benchmarks leaking into the LM training corpus? So that's what I showed you before. Can you dive deeper into how to evaluate multi-turn chats? So multi-turn chats. Oh, yes. Okay, so multi-turn chats is done exactly the same way in the sense that you can, if you use the empty bench, it's the same way as AlpacaEval, which is that you ask the first question, then you provide the answer from the model, then you ask the second question, and then you just ask the LM judge, how good is the entire chat, rather than saying how good is the last answer. So there's nothing, at least when you use LM or humans, there's nothing hard about multi-turn. You just ask now the LMs or the humans, how good is the entire chat? So it's still very subjective, but there's nothing more challenging with this than in the single-turn case. Other question, when we use LM to make evaluation, do we need to fine-tune the judge LM? Okay, that's a great question. So how people do it most of the time is actually they don't fine-tune. So AlpacaEval is not fine-tuned, empty bench is not fine-tuned. You're just using the best possible models that we have out there. So usually either Claude or GPT-N. And you basically prompt. So you say what it should be looking at. So for general domains, this is usually good enough. For expert domains, I think that's actually not good enough. So as you suggest, probably LMs might not have the background knowledge, which is why I would do what I told you before with the rubric eval, where you would have the experts kind of write very detailed rubrics, so very detailed guidelines for every instruction for how to evaluate those. Because the models are actually very good. Given rubrics or given detailed guidelines, they are usually very good at applying them. Other question, can you please explain a bit more the difference between rubric eval and existing LM as a judge setup? Yeah, so the big difference here, because you say Likert scale with language explanation for each score. So the big difference with rubric eval is that the guidelines are actually written for every instruction. So right now, for most benchmarks, you basically have guidelines, for example, for Likert scores that are written for the entire benchmark. So it's like, oh, you should be considering, you should give a 5 if the model is if the output is good. But then what does good mean? So in the case of rubric eval, it's really an instruction specific type of guideline where you're like, okay, good means that this term has to be in the answer, and this term has to be in the answer. So there are some benchmarks, for example, Wildbench, that already has some of checklists, but they are really not very specific. So actually, I didn't show it in our results, but you really don't see a big you don't see a big gain from those checklists because they're not specific enough. So I'm basically saying very detailed rubrics where you have experts spend the time to write detailed guidelines. So Oscar asks, when using GPT-4 as a judge, will GPT-4 favor its own output? This is a very good question. It does. So it does, but you might be surprised at the fact that this bias, which we call self-bias, is not as high as what you might think. So for example, we did that for AlpacaEval, where I have GPT-4 ranking 5 different models. Then I have Claude ranking 5 different models. And I have, I forgot which one, Mistral, I think, ranking 5 different models. And you see that actually they all agree, at that time at least, that GPT-4 was the best model. So even though there's a self bias, they can still prefer the other models. Another reason why I don't think it's that much of an issue is that it only biases for a single model. So right now, for example, AlpacaEval has 200 models or even more on the benchmark. Like it only means that there's a bias for one of the 200, which I think is not that bad. Plus, as I said, it's maybe not as strong as what some might think. Next question. If the model is contaminated by the dataset, how do you tell what the model learns from fine-tuning versus what is already known from pre-training? Or should you just try and avoid that benchmark entirely? That's a good question. Yeah, I've never seen work on that. I don't think you can know besides try again the fine-tuning on a different benchmark, on a different, data set. That being said, usually fine tuning is not done on really like data sets. On benchmarks. So the reason why there can be contamination, I don't think any companies really want to have contamination. What ends up happening is just that they download as much of the data as possible that is, for example, on GitHub. It just happens that like the AlpacaEval instructions on GitHub. So if they are not very careful about removing those instructions or this data set from the pre-training corpus, then they will actually have this issue of training or pre-training on the test set. But for fine-tuning, usually it's a much smaller subset. You only do fine-tuning on maybe max 1 million, but usually like at least in the open source community, less than 100,000 examples. You know very well which data set you're fine-tuning on. So I think you never basically fine-tune on your benchmark besides if you actively try to cheat the benchmark. So next question. What are the potential future research directions for creating such benchmarks? Great question. So as I said, I'm really excited about kind of this rubric eval way of thinking, which I would just broadly say it's basically human in the loop. So I think right now I talked about LLM doing the evaluation, but I really think we need to have humans in the loop, even more so when you put models in production. And it's like, how do you best make LLMs collaborate with humans to make these benchmarks more scalable, but also higher quality? I think rubric eval is just one potential approach. There might be others. Another thing which I excited about for benchmark for research direction in this kind of LLM based benchmarks is that right now I only talked about LLMs that are used for defining a metric. But I said that the instructions are kind of fixed. But that's not how we do it as humans when we interact with a model. If I want to know whether a model is better than another one, I will basically ask some questions and try to search cases where the model is bad at. And I would love to see more work where LMs try to generate the instructions that will basically find what the model is bad at and what the model is good at. There's already some work in adversarial red teaming, but it's a little bit different because it just tries to find the cases where your model is terrible at. I think what you should be really thinking about is when you do a benchmark is you should be thinking about kind of searching such that you can find in fewer cases the real score of your LLM. So another way, how I view it at least, is that you try to estimate this expectation, and you want to use something like a importance sampling for like lowering the variance of your expectation estimate, and you can do that with other LLMs. I have a bunch of ideas for this, but I'll move on for now. Next question. Thank you for the talk. I have a few questions. Could you please share more on the design of the prompt sample base? How to design the evaluation prompt to the benchmark and the target LM to reflect the different dimensional criteria we try to evaluate for. Is there a mechanism to automate the prompt generation? Okay, so I'm not sure I completely understand. If what you're asking is the prompt for the LLM judge, then it used to be a lot of work to actually prompt these models. At least, for example, the initial AlpacaEval, we had kind of a few shots, which means we had a few examples of how to evaluate these models in the prompt. honestly, more recent models, the prompt I feel is less important. So it used to be, for example, really important about using kind of like JSON formatting, also the ordering. This is still very important, actually, the ordering of the example in which you give. So I told you have two examples and you ask the model which one is better. It's very important to kind of randomize this order because the model usually prefers the first answer. So generally, honestly, prompt engineering, I think, is less and less important. You just have to make sure that you don't have these type of biases, for example, the order bias. So try to randomize over these type of things. Now your question about generating, automating the prompt generation, there's many work on that. I think there are a few from Toronto. I kind of forgot I think from Roger Gross's lab. I forgot the exact titles of the papers. There are many, but as I said, I think prompt tuning is actually less and less important with these more powerful models. And your second part of the question, how to ensure the low cost of evaluation practice, especially for evaluation based on long prompts. So evaluation based on long prompts, how to make sure that models are cheaper. So the humans will. I've never seen any. Even the more powerful models are always going to be cheaper than humans. I mean, even the ones 1.5 years ago, which were probably 10x more expensive than now, they were already like 10x or 30x less expensive than humans. So I'm pretty sure. I mean, if you have a long prompt, like humans would also need to read a lot. So I'm pretty sure it's always going to be cheaper than humans. At least if you pay them as you should. If you paid them well. So yeah, but how to make sure that you have low cost. One thing you can do is basically try to not have too much of a chain of thought. Honestly, the input prompts, the input tokens are usually cheaper. So try to avoid having very long chain of thoughts. That's what we did with AlpacaEval to decrease the cost. Another thing you should probably be doing is that if you don't want to evaluate your model right now, like I think OpenAI and I think also Anthropic has this thing of batch evaluation or like sorry batch generation at the end of the day where like it divides the cost by 2 or 3x. So yeah, so I don't think it's actually ever going to be more expensive than humans, and it's already pretty cheap. Next. In the LM as a judge paper, you observed that few shot prompting the LM helped improve consistency when dealing with position bias, but also stated that this method increased costs and possibly introduced new. Have you done or seen further work on the impact of few shot prompting can? So just to be clear, I'm not the one who wrote the LM as a judge paper, and it's been a while since I read that one, but that this method increased costs and possibly introduced new biases. Personally, in AlpacaEval, I saw that adding few shot added some biases and made it actually decrease correlation with humans and made it more expensive. So that's why I ended up removing this, and that's why I do everything in zero shot now. So I did not do what you're asking now, which is doing multiple runs of zero shot prompts. I think there's a paper from Cohere that does that, and I would suggest for you to look at this one. I think it's called LLM panel or something like this. Great. Next. Because of the order seems to be so important, doesn't that actually hint that these models don't reason about their input? Or is a specific bias also present in humans? So humans actually have a huge bias for order. So every time you do, for example, you work with MTurkers, you will always randomize the order in which you show things. So yeah, so I think that's also a bias that is present. I think there are probably some work that looked at whether the humans or the LM have this as a stronger bias. I don't actually know, but I'm sure there are some work that analyze that. I do agree with you that hints that there's some lack of reasoning, and I think that's part of the fact that we don't really define per instruction what really we should be looking at. And I'm hoping that things like a rubric eval that say very specifically, okay, you need this and this and this, will improve this type of issue. Also with rubric eval, it's actually absolute, which means that you don't need to have two outputs. So you don't have this order issue anymore. But I agree with you that hence that there might be some issue with these LLMs, which I think is more of an issue of the fact that we're not defining exactly what we want in our evaluation procedure. Next. Sorry, let me see where I was. How to ensure the consistency of a value the given GPT-4 or other LM models may be continuously trained and changed by the service provider. How do you weigh the evaluation generated by different evaluators? So consistency of evaluators, this is hard. I would never compare results from different evaluators in the sense that the correlation is actually pretty high, but I would generally really say that you should stick with the same evaluator. It's true that it's annoying because it continuously retrain with some of the APIs. That's the benefit of using maybe an open source model for evaluation. So that's probably what I would try to do if I really cared about this. Is that I would use kind of like a Llama whatever 450B or 70B, Llama 3, and then you know that it's always the same. So yeah, that's what I would do. That said, I actually in AlpacaEval we have very high correlation between using different if you compare the ranking given by different LLMs, as long as the LLM is like strong enough. But it's true that like the actual absolute number will change, but the ranking usually doesn't change by that much. So if you really care about the ranking, if you really care about the absolute score, then I really think you should not be using something like AlpacaEval, the Wild Bench, or Empty Bench. I think you should be using something more based on Likert scores that is very well defined, something like what will end up being Rubric eval, hopefully. How does saturation happen? Good question. I mean, there are two things. One, the models are getting just better and better so quickly. So that's like one possible. It's just that the models are getting so good that it saturates these benchmarks. That's one possible issue. Another one for at least for the for the most used benchmarks like MMLU. Oh, I think there's a hard stop now. Okay. You feel free to ask me questions online, or I think the video will be on YouTube, so you can also ask questions there, and I will try to continue answering there. Thanks everyone for coming, and I think there's a hard stop, so we should leave it there.
Yann, thank you so much for your time. We really appreciate it. And yeah, if anybody still on the Zoom has if anybody has any further questions for Yann, please feel free to reach out to him directly. Thank you, Yann.
Great, thanks. Bye. Thanks for the invite.